Coming at you right now, subtopic 4.2 Covalent Bonds Part 2. Let's share some more. So, how do we draw molecules? To answer that, we need to ask our good friend Dr. Gilbert Newton-Lewis, aka Mr. Awesome Chemist. He's Mr. Awesome Chemist because he came up with some very important theories and ideas, including how covalent bonding works, Lewis acid-base theory, the Lewis dot diagrams, some important contributions to chemical thermodynamics. The guy even made the word photon. He's just awesome. First, we're going to learn about Lewis structures, also known as Lewis dot diagrams. We can see from our IB syllabus that we need to learn how to draw these for molecules and ions of up to 4 electron pairs on each atom. So let's get right to it. First, we need to learn the octet rule, and this is the tendency of atoms to form a stable arrangement of 8 electrons in their outer shell. This is the arrangement that the noble gases have in their outer shell. If you're in high-level chemistry, you might recognize this as an S2P6 configuration. There are 6 basic steps to drawing Lewis structures. Let's work through them with water. First, we need to count the total of valence electrons. There's 8 for water, 6 from oxygen in group 6, and 2, 1 each, for the 2 hydrogens from group 1. We draw the skeletal structure, oxygen in the middle and hydrogens on the side. We assigned 1 covalent bond between each pair of atoms. Of course, 1 covalent bond is a pair of electrons. Now we add electrons to complete octets. Now hydrogen doesn't get an octet. It can't support one, it only needs 2. And in this case of water, we're now done. We've used 8 valence electrons, and all the atoms in the molecule are happy. They have their full set. Now let's try it again with carbon dioxide. Now we have 16 total valence electrons, 12 for 2 oxygens and 4 for carbon. We lay out the structure and we do our first 2 bonds. That's 4 electrons up front. When we try to complete the octets, we find out we've used too many electrons. We tried to use 20 electrons and we only have 16. How do we solve this? Well, if we double the bonds, that means we're sharing more electrons in those covalent bonds. So now, our 16 valence electrons can make all 3 atoms happy. All 3 atoms see a complete octet. Let's do 2 more examples. First, sulfur dioxide. Now we have 18 total electrons. We lay out the molecule. We start with our first single covalent bonds, add electrons to fill the octets, and now we find that we've used 20 valence electrons, 2 too many. Since it is just 2 too many, if we double just one of the covalent bonds, in other words share 2 more of the valence electrons, now our 18 valence electrons can satisfy the octet for all 3 atoms. Now let's consider ammonia, where we have 8 valence electrons. Nitrogen surrounded by 3 hydrogens, our initial bonds, and we have just 2 more electrons to use, and now we have a full octet for nitrogen and all the hydrogens are satisfied. So what shapes do molecules have, and why do we care? Well, one answer might be enzymes, which are biological catalysts and are fundamental to life. The function of enzymes depends almost entirely upon their shape. Fortunately for us, we only have to consider much smaller molecules than enzymes. To predict the shapes of molecules, we can use VSEPR or VSEPR theory. VSEPR stands for valence shell electron pair repulsion. Consider one atom. If it has 2 lone pairs, 2 non-bonding pairs of electrons, these pairs will push each other away. The same thing will happen with covalent bonds because covalent bonds are made of a shared pair of electrons. If we add in a lone pair of electrons between 2 covalent bonds, it'll push the covalent bonds even farther away. Both of these things, lone pairs and covalent bonds, are called charge centers. The number of charge centers on a central atom determines the shape of the molecule. For example, if there are 2 charge centers on the center atom of a molecule, like beryllium chloride, or carbon dioxide, or C2H2, then we have a linear molecule with a bond angle of 180 degrees. If there are 3 charge centers on the central atom of a molecule, like in boron trifluoride, or formaldehyde, or nitrate, then the molecule has a trigonal planar shape. It's flat, it's in a plane, and it looks like a little bit like a triangle, 3 angles. So the bond angles are 120 degrees. If one of those three charge centers is an unbonded pair, like in sulfur dioxide, then the shape of the molecule is bent or V-shaped, and the angle is slightly less than we might expect, 117 degrees. If the central atom has four charge centers, like methane, then the shape of the molecule is tetrahedral, with the four bonds evenly spaced 109.5 degrees apart. If one of the four charge centers is an unbonded pair like in ammonia, then the shape of the molecule is trigonal pyramidal and the bond angles are slightly reduced, down to 107. If two of the charge centers are unbonded pairs, like in water, then the shape of the molecule is bent or V-shaped, and the bond angle is further reduced down to 105 degrees. To help you get a better idea of a tetrahedron, you might think of tetrapods, the things that they use in breakwaters by the ocean, or sometimes nice cushions for your couch. We can summarize all these shapes in one chart. Here, the light-colored rows are the ones where all the charge centers are bonded pairs, and the dark-colored rows are where one or more of the charge centers is an unbonded pair, a lone pair of electrons. Another pattern to see here is that there are two trigonal shapes, one that is flat, that is planar, with three charge centers, and one that is pyramidal, it really is four charge centers, but one of them is an unbonded pair, a lone pair. There's also two bent or V shapes. One has three charge centers, but one is lone pair or unbonded, and in the other one there are four charge centers, but two are unbonded. Do you remember that covalent bonds can be polar? Well, having polar bonds does not necessarily make a molecule polar itself. For that, we need to consider the molecule's shape. If we consider carbon dioxide, boron trifluoride, and carbon tetrachloride, we see that all these molecules, the polar bonds that they are made of, are all arranged in a symmetrical fashion, so that all those polar bonds cancel each other out. So as a whole, these molecules are nonpolar. On the other hand, if we look at things like chloromethane, or ammonia, or water, all these molecules have non-symmetrical shapes, so their polar bonds do not cancel out, and the molecules are polar. Allotropes. An allotrope is the exact same element, not even different isotope, just exactly the same, but a different structure. And there's three allotropes of carbon. First you have graphite, which is what we have in our pencil leads. Even though we call it lead, it's really graphite. And these sheets of graphite break off really easy because it's weak bonds between the sheets, as you can see. Then there's what's called a buckyball, or fullerene, which should remind you of a soccer ball. And more famously, there's diamond, which has a very rigid, tight crystal structure, which gives diamond its strength. Silicon and silicon dioxide, they're not strictly allotropes because they're different formula, but we're showing silicon doing two different structures. There's silicon, and there's silicon dioxide on the right side. Silicon, of course, is used in computer chips, and silicon dioxide, sometimes called fool's gold, makes a crystal structure. Thank you. The end.